All right, hello, Algebra 1. We are going to start on Chapter 7. Chapter 7 objectives are to write the prime factorization of numbers. So if you remember that from middle school, that will be helpful. And then finding the Gcf of monomials. A lot of times I don't love saying the word Gcf, but because instead of writing greatest common factor every single time, we tend to do that. However, it does tend to get mixed up with greatest common, greatest common multiple. And so because of that, a lot of times GCF and GCM get confused. We're not really going to talk about the greatest common multiple anyway, so we'll be good. All right. If you hear anything in the background, it's because Liam is watching a video. All right. So let's see. So factors are values that multiply to the intended product. And you'll notice that some of these words are underlined, and that's because there is a notes guide that goes along with this video. And so you can go ahead and fill that in. So for instance, factors are values that multiply to be the intended product. So again, you can follow along on that sheet, or you could have printed off the slides like I have. All right, so in that case, factors are the ones that are smaller than the number or equal to. So for instance, factors of 12 that can multiply to be 12 are 12 and 1, 2 and 6, and 3 and 4. So factors are the multipliers. All right. Then we have factors of, for instance, this term. And so all you have to do is break it down into its pieces of 8, and the factors of 8 are 1 and 8 and 2 and 4. And then p squared, which would be a p or a p squared, and then m, which is just m. So if you ever have just a number, we're talking about all of the numbers that multiply to be it. And if we're talking about a term that might have numbers and letters, you break down the number into its pieces, the letter into all of its pieces, and then the m, or the other letter. All right. So prime factorization for any value is the set of prime numbers. A lot of times when I reference prime, especially after this year, we tend to forget what that means. But remember that prime are numbers that are divisible by only one and itself. So for instance, the number 3 is prime, all right, because it can only be divided by the number 1 and then itself 3. So anyway, it's for any value, it's the set of prime number factors that multiply to be the product. So again, here's our definition of prime. Here's the factors from the last example that we had. Remember that 1 times 12 makes 12, 2 times 6 makes 12, 3 times 4 makes 12. But the prime factorization of 12 is actually 2, 2, and 3. Because if we take each of these numbers here, 12 is not prime, 6 is not prime. Generally, even numbers are not prime. And then 1 itself is kind of a special prime because it is divisible by 1 and itself, which is also 1. So either way, if you take 2 times 2, you're going to get 4. And then 4 times the next number, 3, leaves you with 12. All right, so that's your prime factorization. What prime numbers can multiply to be the number that we wanted? So here's the list. A lot of times we'll write this as 2 squared times 3. Just to be fancier. All right. So you've probably seen factor trees. So here we are with our factor tree. And again, you can be following along on the notes guide right here. Prime factorization with a factor tree means that you need to take, for instance, the number 98 and think of any combination that multiplies to get 98. So there's a lot of options, but because it's even, I tend to go with a 2. So in these circles go all the prime numbers, and then you need to know what 98 divided by 2 is. And of course, if you don't know, you can grab your calculator. But half of 8 is 4, and half of 90 is 45, so we get 49. Then you're left with the number 49. Of course, 2 can't be factored anymore, but 49 can be. So you think of what prime numbers, or just numbers in general, make 49, and that's 7 and 7. And again, if you don't know, you can play around on the calculator and find out if 49 is divisible by 3 or 5 or whatever it happens to be. So you can always check. All right. Then we have the prime factorization of 98, and now we get to write these prime numbers. Not this one, because that one's not prime, so we just write 2 times 7 times 7, and that can go here. And remember, to be fancy or save a little bit of space, we could just write that as 2 times 7 squared, because there were 2 7s. All right. So again, if you multiply 2 times 7 times 7, you should get 98. That's prime factoring tree. All right. So the next piece here is to write the prime factorization of each number here. And so we're going to use our factor tree to get there. So using our factor tree in number 40, again, if it's an even number, I start with 2. 2 is already a prime number, so I'll go ahead and circle that. But then 20, which is what makes 40 times, when you multiply 2 times 20, it has to go there. And then 20 has to try to be broken down into more primes. And so again, 20 is even, so at least 2 can go into it. And then we have a 10. And then after 10, 10 is also even, so 2 and 5. And both 2 and 5 are primes as well. So all these little circles are what we would write as the prime factorization. So we're going to write technically 2 times 2 times 2 times 5. But of course, that seems a little redundant, so we can just write 2 to the power of 3 times 5. All right. So when we take a look at the next one, you can't use that idea of if it's even, it's divisible by 2. So if it's odd, you can start dividing by 3 or 5 or 7. And in this case, 3 does divide into 33. And again, if you don't know, you can play around on the calculator or in your head, but remember that you always want to double check. So 3, yes, is divisible into 33, and then we result in 11. And then maybe you don't know that 11 is prime, but it is. And so it turns out that the prime factorization of 33 is just 3 times 11. Since there are no multiples of each of those numbers, it's just 3 to the power of 1, 11 to the power of 1, so we can keep it how it's written. All right. The next one is the greatest common factor, and we're trying to do the greatest common factor between 2 numbers. So thinking of what we did earlier, a factor tree said what could divide into all of these. And then once we look at what are all of the pieces that divide into all of these, what's the biggest thing in this one and this one that go together? The first one that we're going to start with, however, is 12 and 32. So the greatest common factor, the GCF, is the greatest factor that's shared by 2 or more of the numbers of the polynomials. So we'll do number 1 here first, but then we will do one that's a polynomial. So we'll see how that goes. So the first thing you can do to kind of find out what is the greatest common factor of 12 and 32 is taking the number 12 and listing all of its factors, and taking the number 32 and listing all of its factors. Let's say that you don't actually know all of the factors of 32 by heart, because a lot of people don't. All you would need to do is, if you can't do it in your head, take your calculator and start with the number 1. So 32 divided by 1. So we do know that 32 can be divisible by 1 32 times. Then we do 32 divided by 2. And we realize that 2 and 16 are the factors. Then we try 32 divided by 3, because maybe we don't know. But then that means that it's not a factor, because you get a decimal. 32 divided by 4 gets you 8. But then notice that the numbers are getting closer together. So now I only know that the other options are 5 and 6 and 7, because then 8 comes up again. So we'll try 5, and it's a decimal, so it doesn't work. And then 6. And that's a decimal. I guess we didn't try 7, so that's in there as well. But once we get back to one of the whole numbers that we already did, we have every single number, usually half, or in this case, by the highest number you've already got. So again, looking back at all of our results, that meant that 1 was divisible, 2, 4, and 8, and then 16 and 32. So now we're looking for the greatest factor that's shared. So if we look at each of them, the greatest factor in 32 is 32, but it's not in 12, so that's not the biggest one. The next greatest number is 32 is 16, but that's not in this one, so that's not there. The next highest number is 12, and they're not shared. Next highest number is 8, and that's not shared. 6 is not shared. And so the greatest common factor of 12 and 32 is 4. So again, you're just looking for the largest number. Now remember that since it says greatest, we don't want to do 1 because that is not the greatest, it's the least common factor. And then the second one here, number 2, yes, could also be a factor, but it's not the greatest common factor. All right. So 2 methods for finding the greatest common factor. There are actually a lot more, so don't worry if you find another one and it works each time. Perfect, keep it going. So the first one is to list the factors, which is what we already did. So that's what we did in this side, which was list the factors. And then from the list of the factors, we can go ahead and say, the GCF, or the greatest common factor, between 100 and 60 when we look through the entire list. Now 100, here's its factors, and 60, here's its factors. You look through and 100 is not in this list, 60 is not in that list, 50 is the next biggest number, it's not in both lists, 30 is not in both lists, 25 is not in both lists, but then 20 is in both lists. So that means that the greatest common factor of 160 is 20. So again, that's the method that we used in the previous slide. The other way that you can do it is take all of the prime factors, and if there is a matching set, that's going to be part of the greatest common factor. So for instance, the prime factorization of 100.
I guess this one doesn't have any.
Oh, okay.
I guess this doesn't have any buttons.
All right.
Because it doesn't stay to the trailer.
Liam says that this doesn't have buttons.
Because this one doesn't. Because this one has buttons to attach to the trailer.
Okay.
So,
remember, Mama's doing a video. Okay. All right. So anyway, 100 comes from 2 times 2 times 5 times 5. Right? So if I take 2 times 2, it's 4, times 5 is 20, times another 5 is 100. Yay. And then 60, 2 times 2 times 3 times 5. If you look at the list, there's a common set of 2's. So that's going to be in the greatest common factor. Another common set of 2's. 5 and 3 aren't a common set, but 2 5's are. And so 2 times 2 times 5 makes 4 times 5, or 20. Which again means that our greatest common factor is 20. So 2 ways you can list all the factors, or you can take all the pieces, and once we get to monomials, so with letters, this might be the better option. All right. So the next piece here is kind of broken down already, and again, if you're following along on the notes, we have this example listed in there with 15x cubed and 9x squared, and you would put the pieces that we're talking about here. So 15x cubed comes from 15, which has 3 times 5 as its prime factors. And then x can be broken down into either x times x squared or x cubed. So each of these could be a multiple of 15x cubed. In 9x squared, 3 times 3 makes your 9. And x or x squared could be the factors of x squared. So the only thing that's alike in both of these is the 3. And then the largest of these, the largest exponent, is 2. So again, notice that 1 is shared, x to the 1, but we're not going to bring that down as well. We want instead the largest one. Okay, so that means that our greatest common factor is 3x squared, or 3x squared. And so the GCF of 15x cubed and 9x squared is 3x squared, meaning that is divisible into 9x squared and 15x cubed. Okay.
This one
All right.
and I think the bumper. I guess we don't have the bumper.
Okay. All right.
I guess it's still at Oma's house.
Okay. The bumper is at
This one
Oma's
on top
house.
of here.
All right. Thank you, honey. All right. So we need to find the GCF of 12 and 16. And again, if you go back to the previous slide where we did this for just numbers, you could do method 1 where you list them all, or you could do method 2, which does the prime factorization. So I'm going to go ahead and do the prime factorization because that's going to come in handy later. So prime factorization of 12, if we take the approach of doing the factor tree, you can do 2 times 6, where 2 is your prime number, and then 2 times 3. So that means that 12 comes from 2 times 2 times 3. 16 comes from 2 times 8, but 8 is not prime, so we keep going. 2 times 4. 4 is not prime, so we keep going. And so it turns out that 2 to the 4th, there are 4 of them, is 16, or 2 times 2 times 2 times 2. So if we're looking to find out what are the pieces that are alike, 2 and 2 and 3 make 12, and 2 and 2 and 2 and 2 makes 16. And the alike pieces are 2's and another set of 2's, but then after that, nothing is alike. So the prime factor that goes into both of these, the GCF, the greatest common factor, comes from 2 times 2, which is 4. So, of course, taking a look at 12 and 16, you could have probably figured that out as well, but these numbers will get larger, so we do want to just be careful that we're not just guessing and that we're actually verifying that it's true. So 4 is the GCF of 12 and 16. So now we move on to the Gcf of monomials. Okay, and again, it's the same idea. You list out all of the factors, and then you find the matching sets. So the factors of 8x squared, all right, are going to be 2 times 2 times 2. Okay, so again, 8, we're not listing the factors. We're listing the prime factors. So 2 times 2 times 2. And then x squared can be broken down into x or x squared. Basically, you're just listing all of the powers up until you get to the power that's listed. In the next example, which is 7y cubed, we're going to list the prime factors of 7. And prime factorization of 7 is just 7. 7 is prime itself. And then we have y and y squared and y cubed. Okay, and so this is more a list than multiples when it comes to these y's, okay, which is why this is not an equal sign. So if we're looking for alike things, again, 2's are up here and there are no 2's here. 7's, no 7's. X's, no X's. So it turns out that there's nothing necessarily alike. And when there are no matches, that means that the GCF is the thing that goes into all numbers and values. So 1. So anytime that you have no matches, the GCF is going to be 1 because everything can be divided by 1. All right, next piece. A helpful hint, if two terms contain the same variable raised to different powers, the GCF is going to contain that variable raised to the lower power. So we kind of saw that in a previous one. So we said we have 15x cubed and 9x squared. They have the same variable. Again, same variable. The GCF is the lower power. So if we look at the answer, the lower power was x squared, and that was part of the GCF. So that's just your helpful hint so that you don't necessarily have to list them out. And you will get faster at this where you don't have to list them. It's kind of intuitive, but right now, listing is the best so that we can double check. All right. So of course, you're going to have a word problem here. Adrienne is shopping for a CD storage unit. She has 36 CDs by pop music artists, yay, and 48 CDs by country music artists. She wants to put the same number of CDs on each shelf without putting pop music and country music on the same shelf, because that would be a catastrophe. If Adrienne puts the greatest possible number of CDs on each shelf, how many shelves does her storage unit need? So again, she doesn't know. She's shopping for one, so she gets to pick.
I don't know why this needs glue.
Okay.
I don't know why.
Liam doesn't know why it needs glue. All right. So in that case, again, aesthetically pleasing, she's trying to make every shelf have the same number of CDs on it. So we're basically figuring out as what the other problems would need. There are two numbers in here, so we're finding the GCF of these two numbers. Remember that word problems tend to be very much like the problems previous to it, especially in textbooks. So this one here is just asking what's the GCF of 36 and 48 without being as simple. So we are looking for the GCF of 36 and 48. So remember that you can do it one of two ways. You can go ahead and make method one, which is finding the GCF using, the list of all the factors using prime factorization, or prime factorization factor tree. So whichever one you want to do. In this one, I'm going to go ahead and list out the multiples of 36 and 48. This will come in handy later. So the multiple of 36 and 48, turns out that it's always 1 and 36 for two numbers that will multiply, and also 1 and 48 for 48. But then you just go through and figure out what numbers will also divide evenly into 36. So again, in your calculator or in your mind, but of course double checking, 36 divided by 2. Does that work? And that's 18. So that means that one of the other factors sets are 2 and 18. Then we continue on and we do 36 divided by 3. And 36 divided by 3 is 12. So we can do 3 and 12. And then looking at how I'm doing this, we notice that the only other options are going to be between 3 and 12. So 4 through 11 could be options divisible by 36, or divisible into 36. Then we try 36 and divide that by 4. That's the next number. And we get 9. And then we can continue on and do 36 divided by 5. But notice that 36 divided by 5 gets a decimal, so we don't want to use that one. And then 36 divided by 6 is 6. And so you might think that you would write 6 twice, but really once in the list is fine. And then after that, we have found all of the pieces. You can try 7 and 8 if you want, but they will not divide into 36. All right. Then for 48, we do the same thing. So we go from 48 and we say, is it divisible by 2? Yes. And it's 24 times. And then we ask, is 48 divisible by 3? And you might think not because it's an even number, but it is. And for some reason at this exact moment, I'm not sure. So I'm just going to do 48 divided by 3. Hey. All right. It's 16. So then we continue on and we say, I wonder if 48 is divisible by 3, going along these numbers here. And 48 divided by 4 is going to be 12. All right. Then we move on, and 5 does not work in 48. 6 does. 6 times 8. So we're going to squeeze in a 6 and an 8. And so these are all of the numbers that are divisible into 48. So remember that we are trying to find the GCF. So that means that we're trying to find the largest number. So going through, for instance, the numbers in 48, this is not in here. So 48 is not the GCF. 24 is not an option in there. 16 is not in there. But then once we get to 12, it is in both of them. So 12 is the largest number in both of those, which in this word problem means that each shelf needs 12 to hold 12 CDs. All right, so there it is. So again, this time I decided that I would use the method where you do the list of factors, but in the previous ones, I've done prime factorization, but of course either of them works. Alrighty. The last page here is an exit ticket asking you to write the prime factorization, find the GCF, or find the GCF of each pair of monomials. So if you would like to take the time to do this, remember there is an assignment as well to kind of practice what's going on. But if you continue watching, I will work through each of these so that you can have more examples to look at. So the prime factorization of 50 in number 1 here is breaking it down into its pieces. So for instance, 2 times 25. 2 is prime, so that one stays, but 25 is not. And that's 5 times 5. So that means that a 2, a 5, and a 5 are going to be my prime factorization. It's nice if you write them in least to greatest number and then use powers if you can. So 50 is 2 times 5 squared. We're going to do the number 84 the same way. So number 2, we're looking for the prime factors of 84. Breaking that into its pieces, we have 2 and 42. And 2 is prime, but 42 is not. So we break that further down into 2 and 21. And then we break that into more primes, 3 and 7. So that means that 2 times 2 times 3 times 7 is actually 84. And again, I'm not going to write 2 times 2 times 3 times 7 just because that's pretty redundant. All right. Then looking at the next piece, we're going to find the GCF of each pair of numbers. So I'll do number 3 in the method 1, which was listing them, and I'll do number 4 in the prime factors. All right. So in number 3, I'm going to go ahead and do... Yeah, honey, it's over here on the table. All right. So 18, if I list all the factors that multiply to be 18, remember that 1 and 18 are clearly the first pieces. Then you see if the next number, 2, goes into it, and it does, to get 9. And then you see if 3 goes into 18, and it does, you get 6. And then it turns out after that, 4 does not go into 18, 5 doesn't go into 18, and then we get back to 6. So those are all the factors, the listed factors. And then the other number was 75. And again, we're going to find the greatest number in this list that matches the greatest number in this list. So we have 1 and 75. 2 does not go into 75 because it's an odd number. 3 does go into 75. And again, if you don't know, you can always be dividing with your calculator. 4 does not go into 75. 5 does. 5 goes into 75 15 times. And then we check if 6 goes in. Nope. And 7. Nope. 8. Nope. 9. No. 10. Nope. 11. Nope. 12. 13. 14. Turns out we get all the way back to 15 again. So the only factors of 18 and 75 are this list. And then we go through and find out which things divide into both. So 75 is the highest number here, and there's not one there, so that is not the GCF. 25 does not exist in here, so no. 15 is not in both. 5 is not in both. And so the first number that's actually in both of these is 3. So that means the GCF of 18 and 75 is 3. And remember that sometimes it could be as low as 1. All right. So then we're going to use the other method for number 4. So number 4, we're looking for the GCF of 20 and 36. All right, and that was pretty terrible handwriting. Okay. So we are now going to find the prime factorization of 20 and 36. So we can do a factor tree, or you can kind of do it in your head, but 20 is broken down into 2 and 10, and then 2 and 5. And so I know that 20 is 2 times 2 times 5. Then I'm going to find if I can get sets that match from 36. So 36 is 2 and 18, 2 and 9, and 3 and 3. Careful with odd numbers, because a lot of times, since we think most primes are odd, that you kind of just stop at an odd number. But 9 is, of course, not prime, because 3 times 3 will make 9. So that means that our prime factorization is 2 times 2 times 3 times 3. And we are trying to find the pairs that match in both of these. So in that case, we have a 2 in both of them. So a 2 here and a 2 here. But then the other sets, 5s don't match with 3s, and so those don't get to count. So when we come up with the GCF for this, it's going to be from 2 times 2. And so the GCF is 4. So going back over here, 4 is our answer. Just getting rid of the glare there. All right. So the next two problems are finding the GCF of each pair of monomials. So if we go through finding that, remember that we are going to list them kind of like we did here, only now there's going to be variables involved as well. So in number 5, we are looking at 12x and 28x cubed. And so if we list the prime factors of 12, the idea would be that you would do a factor tree, or you can know that it probably has a 2, and then a 2 times 2 times 3 makes 12. And then in 28, you're going to have 2, which will leave you with 14, and 14 is 2 times 7. So this is the prime factorization of 12 and the prime factorization of 28. And then we just list each of the powers of x. And remember that that hint from our notes was that usually it's going to be the highest power of the factors that are there. So going back to the note sheet where it said that. Probably this one. Yeah. So remember that if two terms contain the same variable, which these ones do, x and x cubed, the GCF is going to contain the lower power. So without doing it completely, we can guess that if this has an x to the first power and this is an x to the third power, that in each of the lists, the thing that's going to be alike is just an x. But of course, x cubed can come from x or x squared or x cubed. And so if we look at the list, we realize that x and x are going to be part of the GCF, 2 and 2, and another 2 and 2. So that means that the GCF of these two polynomials is whatever 2 times 2 times x is, which we tend to write as 4x. So that means that the answer to this one is 4x. And then the last one, we're going to do the same thing. We're going to list out the prime factors of each of these. And so in number 6, we're going to list out 27x squared multipliers and 45x cubed y squared multipliers. So 27 is divisible by 3, and then you're left with 9, so that's another 3 and another 3. So 3 to the third is 27. Then we could have an option of x or x squared, but remember the hint, it's probably going to be x squared since that's the lowest of these same variables. Then if we look at the number 45, 45 comes from 3 times 15. And so another 3 and another 5. And again, if you don't know how to do this in your head, you can just make a factor tree. Then we're going to have x, x squared, x cubed, and then y or y squared. So looking at all the pieces that you can pair up, we can pair up a set of 3's, no other numbers. The highest x's are x squared, and then it turns out that y's don't match with anything up here. So the GCF is going to be 3 times 3 times x squared. So 9x squared. So there you have it. Again, the objectives for today's lesson, we're writing the prime factorization of numbers, and then also finding the GCF of numbers and monomials. So hopefully you got that. And now you can watch the video of the assignment after you do the assignment and check to see that it's right.